think you're going to find that if you had success with the last two lessons, that you already understand the concept of a one-sided limit. This is a one-sided limit, and this is a one-sided limit. And I just want to make sure we know how to read this notation. This first one is read, the limit as x approaches 2 from the positive side. And this one is read, the limit as x approaches 2 from the negative side. In both of these, we're approaching positive 2. It's just a matter of which side we're approaching it from. The limit as x approaches 2 from the positive side essentially means we're approaching 2 from the right-hand side. I drew a line with my pencil where x equals positive 2. Let's approach it from the positive side or the right-hand side. As I'm approaching that line from the right-hand side, my graph is headed towards the point 2, 3. So the limit as x approaches 2 from the positive side is positive 3. Let's see what the limit as x approaches 2 from the negative side is. Let me approach it from the negative side or the left-hand side, and as I approach that line, I'm headed towards the point 2, 1. I know it's undefined there, but my graph is still headed towards the point 2, 1. The limit as x approaches 2 from the negative side is 1. Since my right-hand limit and left-hand limit are not matching, we say the limit as x approaches 2 does not exist. Let's look at this next example. What's the limit as x approaches negative 2 from the positive side? Or in other words, what's the limit as x approaches negative 2 from the right-hand side? Well, negative 2 is where the asymptote is. As I approach that from the right-hand side, my graph goes down and down forever. I'm going to say the limit as x approaches negative 2 from the positive side is negative infinity. What's the limit as x approaches negative 2 from the negative side, or what's the limit as x approaches negative 2 from the left-hand side? Well, as I approach that asymptote from the left-hand side, my graph goes up forever. The limit as x approaches negative 2 from the left-hand side is positive infinity. My right-hand limit and left-hand limit are not matching, so the limit as x approaches negative 2, once again, does not exist. We're going to evaluate the limit as x approaches 3 from the positive side, and we're going to evaluate the limit as x approaches 3 from the negative side. I drew a line where x equals 3. As I approach that line from the positive side or the right-hand side, the graph is headed towards the point 3, negative 4. As I approach that line from the left-hand side, the graph is also headed towards the point 3, negative 4. Even though we have a hole in the graph at 3, negative 4, even though the function is undefined when x equals positive 3, the right-hand limit and the left-hand limit are matching, so the limit as x approaches 3 is negative 4. When you're asked to evaluate something like the limit as x approaches negative 3, you're essentially being asked if both one-sided limits are equivalent. Let's first see the limit as x approaches negative 3 from the positive side. Here's where x equals negative 3. As I approach that line from the positive side, the graph is headed towards this point, negative 3, 1. Let's now evaluate the limit as x approaches negative 3 from the negative side. As I approach that line from the left-hand side, the graph is still headed towards the point, negative 3, 1. Since both the right side and the left side are both headed to the same place, the limit as x approaches negative 3 is positive 1. Let's evaluate the limit as x approaches 1. Here's where x equals 1, and let's see if the left side and the right side are headed to the same place. Let's evaluate the limit as x approaches 1 from the positive side. Now, sometimes students get confused with a graph like this. They go all the way to the positive side, and they kind of get lost down here at negative infinity. But when we're approaching 1 from the positive side, here's where x equals 1. We only need to approach it from just a hair to the positive side. We're only concerned with where the graph is right about here. And from the right-hand side, it's headed towards the point 1, negative 2. I know it's undefined there, but the graph is headed towards that point, 1, negative 2. Let's see the limit as x approaches 1 from the negative side. Well, here's where x equals 1. I'll just go over a hair to the negative side, and as I approach it from that side, it's also headed towards the point 1, negative 2. Even though the function is undefined when x equals 1, it has a hole in its graph when x equals 1. The limit as x approaches 1 is negative 2 because the left-hand limit and the right-hand limit are equivalent. Let's see the limit as x approaches 0 from the positive side. Well, as I approach 0 from the positive side, the graph is headed towards this point, 0, 2. The limit as x approaches 0 from the negative side, well, from the left-hand side, it's headed towards the point 0, negative 2. The one-sided limits are not matching, so the limit as x approaches 0 does not exist. We'll evaluate all of these limits algebraically, but we'll also look at them graphically to hopefully increase our understanding. To evaluate the limit as x approaches 2 in f of x, I'll first plug 2 into the function. 2 squared is 4, and 4 minus 9 is negative 5. 2 minus 2, of course, is 0, and negative 5 divided by 0 tells me that this function has an asymptote where x equals 2. Once I determine there's an asymptote at 2, I know the one-sided limits will be either positive or negative infinity. I simply need to determine if they're headed towards positive infinity or negative infinity. Consider the limit as x approaches 2 from the left-hand side. Let's consider what would happen if we plugged 1.9 in. 1.9 squared is approximately 2 squared, which is approximately 4 minus 9 is negative, and 1.9 minus 2 is negative. Apparently from the left-hand side, we're approaching positive infinity. To consider the limit as x approaches 2 from the positive side, let's consider what would happen if we plugged 2.1 in. 2.1 squared, that's approximately 2 squared, or 4 minus 9, which is negative 5. And 2.1 minus 2 is positive. Well, a negative divided by a positive is a negative, so the limit as x approaches 2 from the right-hand side must be negative infinity. The one-sided limits do not match, so of course the limit as x approaches 2 does not exist. Let's take a look at the graph of this function, x squared minus 9 divided by x minus 2. You can see as we approach 2 from the left-hand side, we're headed towards positive infinity, and as we approach 2 from the right-hand side, we're headed towards negative infinity. To evaluate the limit as x approaches 4 of g of x, I'll first plug 4 into the function to get some information about its behavior at that point. 4 squared is 16, 16 minus 16 is 0, and 4 minus 4, of course, is 0. 0 over 0 tells me the function has a hole at that point. And if a function has a hole in it, that tells me there is a limit. The left side and the right side are converging on the same point. I can express x squared minus 16 as x plus 4 times x minus 4, and then the x minus 4s will cancel out. The limit as x approaches 4 of g of x is 4 plus 4, or 8. That means the limit from the left side is 8, and the limit from the right side is 8 as well. Let's take a look at the graph of x squared minus 16 divided by x minus 4. We're evaluating the limit as x approaches 4. When I trace 4, this function is undefined at 4 because it has a hole in it at 4. At 3.999, it's essentially 8. At 4.001, it's essentially 8. The function h of x is what we call a piecewise function. It's broken into two pieces. This graph is a line when x is less than 1, but then it's a parabola when x is greater than 1. The graph takes on the shape of 4 minus x on the left side of 1, and the graph takes on the shape of 4x minus x squared on the right side of 1. Therefore, the limit as we approach 1 from the left side, we can just plug 1 into this left-hand piece. 4 minus 1 is, of course, 3. As we approach 1 from the right-hand side, we can simply plug 1 into this right-hand piece. 4 minus 1 is 4, and 4 minus 1 squared, 4 minus 1, is also 3. The left-hand limit is 3, the right-hand limit is 3, so I know the limit as we approach 1 is 3. Let's graph this one on our graphing calculator. This function is 4 minus x when x is less than 1, plus 4x minus x squared when x is greater than 1. You can see it's a line on the left side of 1, and it's an upside-down parabola on the right side of 1. If I trace 1, this function's undefined because the function only exists when x is less than 1 or greater than 1. The function does not exist when x is equal to 1. But if I go a hair to the left of 1, if I trace 0.999, I get essentially 3. And if I go a hair to the right of 1, I get likewise essentially 3. The hole in this graph is at the point 1, 3, so the limit as x approaches 1 is 3. In example number 4, we have another piecewise function. It's x plus 2 on the left side of 3, and it's 2x minus 3 on the right side of 3. To determine the limit as x approaches 3 from the left side, I'll simply plug 3 into this left-hand piece. 3 plus 2 is 5. To determine the limit as x approaches 3 from the right-hand side, I'll plug 3 into the right-hand piece. 2 times 3 is 6, and 6 minus 3 is 3. The left-hand limit and the right-hand limit do not match, so the limit as x approaches 3 does not exist. Let's type this one in our graphing calculator. It's x plus 2 when x is less than 3, plus 2x minus 3 when x is greater than or equal to 3. And perhaps you can see that these pieces do not come together where x is 3. As we approach from the left-hand side, we're headed towards the point 3, 5, and as we approach from the right-hand side, we're headed towards the point 3, 3. The limit as x approaches 3 does not exist.